Welcome back to ECE 442-542. In this video we are going to prepare for the second attempt of quiz number 7 based on questions from the first attempt of quiz 7, and we will work through those to try to help you gain some proficiency in attacking the problems on attempt number 2 for quiz number 7. And we will address these questions in the order that presented the most challenge to the class. This first problem then is to select a controller or controllers C of Z that will stabilize the plant G of Z for a given gain value. So we're not worrying about the gain value. We just want to know, in this structure of a controller, can we stabilize the system? And all of these controllers now are working with the same plant. The plant has a pole at 1.5. It has a pole, it has a 0 at 1.5. It has a pole at the origin, and it has another pole at 1. So this is actually a non-minimum phase system, and I'm already showing you the answers, so let's try to justify why those top two are indeed valid answers and the bottom two are not. Let's deal with this one first. For a non-minimum phase system, in this case, since that pole at 1 is right on the stability boundary, there's no way that that particular, so this is for this is for C of Z, our controller being a non-negative value K. So I should have said for a given K where K is greater than or equal to 0. And then the other branch of our root locus goes to the left. We have two branches. This particular controller structure does not work. There's no way that you can have a stable closed loop system for a constant gain controller. So that one is out. The other one, let's say from the bottom, let's just continue with our original system. And now we, with the controller, are putting another pole at the origin and a 0 on top of that pole. Well, if that pole wasn't on the stability boundary, this might be getting to be an okay choice, but because that pole is on the unit circle to begin with, we can't cancel anything, poles or zeros, that are either on the unit circle or beyond the unit circle. So in this case, this particular controller structure, since we are now having a 0 at 1 with a pole at Z equal to 1, this is now going to be what we disqualify that controller on that basis. We can't cancel poles or zeros on or beyond the unit circle. Now, not to confuse you, well, let's continue then with this particular problem and try to find why those first two choices are valid for stabilizing this particular system. Our system, again, had a pole at the origin, a pole at 1, and a 0 at 1.5. The next choice was to go ahead and place a 0 outside the unit circle at 2 and a pole at 1. So I didn't say we couldn't locate poles and zeros beyond the unit circle or on the unit circle. We just can't place them on top of another pole if it's a 0, or another 0 if it's a pole that we're canceling. We could have placed this 0 there. That would have been okay because we're not canceling that 0. But here is what we have, and we also, I think, placed a pole at the origin in this particular controller. And now what I want you to do is sketch the root locus. We know there's branches on that line segment of our root locus. We know that there's branches. There's actually 2 branches here, and there's a branch there. All of those, so we have, what is happening? Well, at large K, we'll eventually be approaching those 2 finite zeros, and one of our closed loop poles will zip off to negative infinity. So we can't go too high on the gain, but we didn't say that we need to stabilize for all K. We just want to be inside the unit circle for some range of K. And in this case, if we keep K small, these 2 are going to go towards each other from between 0 and 1. This one at the origin, one of those goes left, one goes right. As long as we keep the gain smaller than either the gain to get us to -1 or the gain that will place us outside the unit circle here. We don't know, and we're not needing to calculate what the gain is here, let's say K triangle, and what the gain is here, K -1. We would determine, if we needed to, the maximum K for stability based on the smaller of K delta or K -1. But this particular controller, where this controller C of Z was some K, Z -2 over Z, that's okay. That one works. One more. This last controller to investigate has a 0 at 1.5, and I said that's okay. What we do beyond that may invalidate, but that's okay. We're not canceling anything outside the unit circle. And then we had a pole at 1/2. Hopefully what you can see then is this segment of the real axis does not belong on the root locus because we have an even number of poles and zeros to the right. This segment does belong, and that segment actually contains 2 branches of our root locus, and this segment belongs. Now, as long as we keep the gain small and don't crank up the gain so much that these 2 branches exit the unit circle, or this pole exits the unit circle, again, we're looking, if we needed to, we don't need to for this problem. For this problem, all we're looking for is confirmation that we have some range of gain that will allow 3 branches of our root locus, all of our root locus branches, to be simultaneously inside the unit circle. And in this case, we can find some gains. They may not be very big, but we could then check, if we needed to, the gain values at K box and K delta. We would find the smaller of those, and then we would have a stability from 0 up to K max, where K max might be K at -1, or it might be K at triangle. But either of those, we can establish a K max, and where was this one? This was now at 1/2. So this one is also okay. Next question. Select the controller C of Z that will stabilize the plant G of Z for a given gain value K. So this is another stability question. Now our system, in fact, is a little different. Now it's actually an unstable open loop system because of that pole at 1.5, and we have a 0 at 1/2. Well, if we look at this just with a constant gain controller, then we need to investigate what's happening at this particular value of gain versus this gain. If the gain to get us inside the unit circle on the right is smaller than the gain to get us outside the unit circle, then this controller would be okay. Or in this case, we now need to find, using this CG magnitude condition equaling 1 for a constant gain controller, we solve that for k, and we have z times z minus 1.5 over z minus 1/2. And we now evaluate that at 1, and we have 1. This is now 0.75. What am I doing? 1 minus 1/2 is 1/2. And then we divide by 1 minus 1/2, which is 1/2. Worrying about the magnitude only, and this becomes 1. What's the gain at minus 1? We have 1, then we have 2.5, and we then have 1.5. And 2.5 is a little bit bigger than 1.5, so in fact, because of that, we now have this 5/3 or 1.67, so we do have some range of gain k that will allow us to be stable. The stability then would be between k at 1 with k at minus 1 for that particular controller structure. So a non-negative k would produce a stable closed loop system. Let's look at the top one. We have, and here I'm really asking you to look at or examine the root locus structure for these various scenarios. We have a pole at the origin, we have a pole at 1.5, and we had a 0 at 1/2. The top one now says, oh, let's place a controller 0 at the origin, and that's okay. We can cancel poles and zeros that are inside the unit circle, and usually we want them to be within a fair distance within the unit circle. So now let's say, okay, we're going to be okay as long as we're canceling poles and zeros here. We just don't want to be teasing that stability boundary with our pole zero cancellations. And where was our other pole? We had a pole of our controller at 1. Well, now we have our story that everybody enjoys. We have 2 poles to the right of a 0 because that pole zero cancellation, you can essentially put on your glasses and not even see that, and now you have this coming around, and what is that going to be? Well, that radius, so you would want to check this radius. This was now 1.5, I believe, where we began. So now we have a radius on that circle determined by the geometric mean of the distance from the center of the circle, which is at 1/2 to 1. So that's 1/2. And the other length in our geometric mean calculation is the distance from 1/2 to 1.5, or that's a distance of 1. So this is now 1 over the square root of 2. Or that's the square root of 2 over 2, or that's now this 0.707. That means that we'll be coming in here at 0.3, roughly, and we're departing or breaking away from the real axis 0.707, or a radius distance away from that center, which is at the 0. So this is going to now come over here. And we do have values of gain k that produce a stable closed loop system. Now we need to crank up the gain to get us inside the triangle. Those are supposed to be conjugates of each other. and then one of these would go to that finite 0, another would go outside there, and then we have to reduce the, or keep the gain less than k box. So here's k triangle, here's k box, but this controller structure, what was the controller structure? C of z was now z over z minus 1 times k. That's okay for k between k triangle and k box, and we didn't need to calculate k triangle or k box. So we've now verified those two. Let's see why the other two don't satisfy or stabilize this system. Again, our system, let's write that down or draw that. And that now was a system that had a, forgotten again, a pole at the origin and 1.5. This was an unstable system. And a 0 at 1.5. Here, C of z, we want it to be k 1 over something. And where was the something? It was now a pole at z minus 1. So this controller is now saying, oh, let's cancel that and put a pole here. Now you can't throw away your glasses here or put them on and say, oh, this is fine, this is fine. That's not fine. That's what's going to cost you 150 points on this 10-point problem. So that is not going to work. That is an unstable that produces, because in your internal stability argument you will find that you do have a closed loop pole maybe between your disturbance and the output at 1.5. So that's not going to work. That you don't even have to do anymore. You can just say, oh, they're trying to do an unstable pole zero cancellation. That's not allowed, so I'm not going to go any further. The next one, controller-wise, is now k times a 0 at 1.25 and a pole at 1. So now we have a 0 here and a pole there. And let's draw our root locus. That immediately says we have now fixed a closed loop pole between 1.5 and 1.25, and will never, for k non-negative, remove that unstable pole outside the unit circle, even though we have these others that could be stable. So this C of z with a 0 at 1.25 is also not going to be producing a stable closed loop system. That's why we wouldn't check that one. Now select the correct root locus arrival angles towards the 0 in the upper half of the complex z-plane associated with g of z, and select all angles that are correct. The angles are measured counterclockwise with respect to a horizontal line extending in the positive x direction. That's how we measure all of our angles. This is now really just asking us for an arrival angle. If you do the factorization, the numerator has roots at plus and minus j. Those are now at, and maybe I won't even label those, my diagram will get too busy. We have zeros at plus and minus j. We have poles because of the factoring of the denominator at plus 1 and minus 1. We now are trying to determine how the root locus will arrive, in what direction will the root locus arrive at this particular 0 in the upper half plane. And what are we calling those? Alpha sub a for arrival. Now we simply do our phase angle condition. We measure this angle, and I've tried to lay this out so that you can quickly see what these angles are. You have this angle, let's call it theta p1, that's at 1, and let's just call this angle, looking from this twisting all the way until we see that 0, let's call that theta sub z. Our phase angle condition then says that the sum of the 0 angles minus the sum of our poles is equal to minus 180 degrees. We can determine all of these angles except alpha A, so we have one unknown. We can solve for that. Alpha sub A is now minus 180 degrees minus theta sub Z plus theta P minus 1 plus theta P 0, taking those other angles over to the other side of our equality sign. Alpha sub A then is minus 180 degrees minus theta sub Z is 90 degrees. That's looking straight up to that 0 in the upper half of the Z plane. Theta P sub minus 1 is 45 degrees. And theta P1, because of the up 1 over 1 geometry, gives us 135 degrees. This is canceled by that, and we're left now with alpha sub A equaling minus 90 degrees. And if all of the angles were positive, then maybe you do, in this case, have to say none of the given answers. What this is saying is that the root locus is approaching, and you could have even drawn the root locus. You know that you have a segment there. This one goes there, and these zeros are just attracting those branches. If you would have drawn your root locus, you could have seen another way of finding this answer just from that sketch, and you say, wait a minute, the only angle that can come into that 0 at is when alpha sub A, measured relative to the positive horizontal, is minus 90 degrees. Next question. For the given plant G of Z, which PID controllers will yield a stable closed-loop system for some non-negative gain value K? Again, we're dealing with non-negative K values. The hardest part of this problem, the plant stays the same. We have two stable poles, one at 1/2 and one at 1/4. The hardest part of this problem is factoring these numerator polynomials in the given controller expressions. The top one, if you factor this one, you will see that in fact that is now going to be, that 0.1875 is 3/16. So this numerator is producing a pole here, a 0 at 1/4, a 0, at 3/4. We have a pole at the origin and another pole at 1. So in this case, if we draw the root locus, we now have these two coming off. We don't need to worry about where they are going asymptotically in terms of where that centroid is located, but we just need to determine that in fact there is a range on K that will allow this pole to be inside the unit circle at the same time as these two. We are restricted on our gain. As soon as we cross or go beyond that unit circle, then we can't crank up the gain anymore, but this particular controller is fine. The next one, if you factor that numerator, it's now giving you a 0 at 1.5 and another 0 at 1, so that now our particular pole 0 diagram, we started with a pole at 1/2 and, is that right? And 1/4. We now, for this second transfer function of our controller, are introducing a pole at the origin and a pole at 1, and a 0 at 1.5, and a 0 at 1. And you could sort of say, wait a minute, what are we doing here? We've now introduced this pole 0 cancellation, which you could really kind of do, because those are internal to this controller, and you would cancel those prior to even implementing this controller. So that's really okay. What's giving us, well, it's not really so okay. Maybe I should take that back. This now is going to, maybe I'm not so keen on this particular answer. So maybe this one would have been okay to be stable, because you can now have, I'm not sure why I let that go through, because this one now is having this cancellation, and again, you could do that internal to the controller and not ever realize that. So effectively your controller here is now this k z minus 1.5 over z. And that's actually going to be, for a limited range of k, stable. So maybe I need to go in and give students some credit for this one, because you could have 3 poles simultaneously, because what I said, this is internal to the controller. We wouldn't even put that in our controller. So let's just go ahead and go back and figure out that that one needs to be sort of thrown out, or given you credit for that one. So let me go back and redo the grades maybe. I hope I can do that, and see what your scores are for that particular problem. So let me make a note of that. The only one that is really not a valid solution is none of the given answers. They're all actually valid in this particular case, but this one now has zeros at 1/4 and 1/2. So these are actually canceling the original, whoops, poles, and they are introducing a pole here and a pole there. And in this case, then, this comes to the, one goes to the right, one goes to the left, they meet halfway between, and there is a valid range of k for stability, so that one's okay. The last one is now going to be having roots that are complex, but that's okay. Can be okay. In this case, let me give myself a little bit more space. We now are putting a pole at the origin and a pole at 1, and we're putting zeros at 1/2 plus and minus j 1/2. And in this case, then, we have those two branches going towards each other and breaking away. We have these two branches, and it really doesn't matter, but we could verify this. These two, let's say, go to that complex 0 pair, and these then go zipping off. We don't need to calculate the asymptote centroid for any of this. We do know that we do have the opportunity to have all 4 of those poles simultaneously inside the unit circle. Those wouldn't have had to be there. Those could have been here and here for a given gain value, and so this last controller is also valid for stabilizing the system. Next question. How many root locus asymptotes exist for the given g of z? Well, how many asymptotes are there? Well, the asymptotes correspond to, we have as many as we have pole 0 excess, or that's the same as the number of zeros at infinity. And in this case, we have no finite zeros. The pole zero excess, which I think notationally we've been calling pz sub e, in this case, pz sub e is 3, and so our number of asymptotes that we have, or that exist, what some people may have sort of just quickly forgotten about is we have a pole here, and we have another 2 poles somewhere. We could find where those are. It doesn't really matter where they are. Those are now at going to be z minus 1 and z minus 1/2 if we factored that second quadratic. And so our root locus diagram, what you may have forgotten is, in fact, this is an asymptote. We have an asymptote that's approaching, and we have another asymptote that's approaching. So we have 3 asymptotes. The answer for that question was 3. Some people put 2 because maybe they forgot that that is actually an asymptote going off at minus 180. And the number of asymptotes that we have is going to equal our pole zero excess, or if you think of it better another way, you can say how many zeros do I have at infinity? That's how many root locus branches are going to be going towards those infinite zeros, or zeros at infinity, and that's how many asymptotes we actually have. Next question. Find a gain value k that will locate closed loop poles at 1/2 plus and minus j1/2 when the plant and the controller are given by this set of transfer functions. We have a plant that has a pole at 1/4 and a pole at 3/4, and in fact it looks like we have zeros canceling those, and we have poles in our controller at 1 and the origin. And we want to know what's the gain to get us to that particular triangle, and we know that triangle belongs to the root locus because really with our glasses on, those pole zero cancellations, which are allowed because they're inside the unit circle, we don't even need to focus on those, and we now have our root locus going through 1/2 plus and minus j1/2. We want to calculate the gain to get, to get us to that triangle, which is really going to involve those lengths being multiplied together and divided by any gain value that we might have, and somebody might have forgotten that the plant itself possessed a gain constant other than just 1. So in this case, we can now find the k to get us to that point by using our magnitude condition. In this case, we now have 0.5 over that's our plant. We have a controller whose zeros cancel the plant poles, but that's allowed since those cancellations are occurring inside the unit circle. We can solve that for k, and now we have k is the magnitude of z times the magnitude of z minus 1 over, and this is what I think some people forgot, over that constant, which is 0.5, and we want to now know what is k triangle. Well, that will be found at z triangle, which is 1/2 plus j1/2. We plug that value in for z everywhere. This one is in fact going to have the same magnitude, and you can see that graphically. The distance from the origin to 0.5 plus j 0.5 is exactly the same. That hypotenuse is the same length as the distance from 1 to 0.5 plus j 0.5. So in this case, our k delta is going to be, this produces a 2 in the scaling factor out front, and we have then 1/2 squared plus 1/2 squared, square rooted, times that same expression, maybe minus 1/2 squared plus 1/2 squared, but we're squaring that. So we really have 2 times 1/4 plus 1/4, or 2 times 1/2, which is 1. And that's the answer for this particular problem. If you had forgotten this 1/2, then you would have ended up with a k delta of 1/2 and probably gotten the answer incorrect, because I probably had that as one of your choices. Now we want to consider a plant g of z controlled with a PI controller. Locate the 0, which is this value there, in the PI controller to yield closed loop poles at 0.6 plus and minus j 0.1. So in this particular case, we have a pole at 1/2. We have a controller pole at 1, and we want our closed loop pole to go through that location of 0.6 plus j 0.1. If we just wanted the root locus of this combination, we know that these would come together and separate halfway between, and so we would have our real part of 0.75. That we want a little bit to the left, and so we can't just cancel that pole there, but we probably are going to have a 0 to the left of that pole. And now we can use the phase angle condition to determine the angle that that 0 makes with respect to that closed loop pole location, or with respect to delta. Here, let's say this is theta p1. Let's call this angle of the second pole theta, what do we want to call it, p sub 2, and then we have this angle, which is theta sub z. Our phase angle condition then says that theta sub z minus all of our poles angles needs to equal minus 180 degrees for that point on in our z-plane to belong or live on the root locus. We can calculate theta p1. Theta p1 is 180 degrees minus this acute angle, where we're going up 0.1 and across 0.4 from 1 to get to that 0.6 plus j 0.1. This is not a very big angle. It's actually a little bit bigger than 14, so this, now we end up with 165, almost 166 degrees. Theta p sub 2, though, I hope you can see that theta sub p sub 2 is 45 degrees. We go up 0.1 and over 0.1, so I located that triangle in a nice location for theta sub p sub 2's calculation, and now we can solve for theta sub z. Theta sub z now, adding the pole angles to both sides, we have minus 180 degrees plus 165.96 degrees plus that 45 degrees, and doing the algebra ends up with about 31 degrees for theta sub z. We're not quite finished. Now we need to use that information. We know our triangle is sitting there, which has a real part of 0.6. We know this distance vertically is 0.1, and we've just determined this angle, theta sub z, and we're trying to find where is alpha. And now we can, I hope you can see that using trigonometry we can solve for x, and x then noting that alpha plus x is 0.6 will produce the alpha value. In this case, the tangent of theta sub z is how our vertical change, 0.1, over our horizontal change, which is what we're trying to find, which is x. X is now 0.1 divided by the tangent of this 31 degrees. X now ends up being 0.167. Let's just say it's 0.1. Now we know then that alpha is equal to 0.6 minus x, or this is now 0.07 less than 0.5, or this is now 0.43. That's where our 0 would need to be located in this PI controller to produce closed loop poles at 0.6 plus and minus j 0.1. This problem, let's select the correct root locus departure angles from the pole in the first quadrant, and now we need to factor this denominator. This is in fact going to be complex conjugate poles at 1 plus and minus j1. We now know where our poles are. We have a pole at the origin. We have a pole at plus 1 plus j, and we have another one at plus 1 minus j. We are now wanting to determine what is the departure angle, what's the root locus look like, how is it departing from that particular pole. And I hope you can see that you can now measure this angle, theta p0. We can measure this angle, and we can add in the alpha sub d. Our phase angle condition now says that alpha sub d, we don't have any zeros, so we have nothing minus the sum of all of these pole angles equaling minus 180 degrees. We can now take the alpha sub d, or add it to both sides, and add 180 to both sides, and we now have 180 degrees minus theta p sub 0 minus theta p1. Those angles are, I think, fairly clean to determine. Theta p0, we go up 1 and over 1, that's 45 degrees, and we're subtracting that. Theta p sub 1, we're looking straight up, or that's now 90 degrees. We are now taking 180 minus 90, that's 90, minus 45, so this is now 45 degrees. Identify the centroid location of the asymptote angles associated with the root locus branches of g of z that go off to infinity when g of z, and now we need to factor g of z, but this denominator factors into poles at 1 and minus 1 and 2 at the origin. We actually have 4 poles. There's no finite zeros. We have 2 poles here. We have a pole here and a pole there. And what are we wanting to know? Identify the centroid location. So now we want to find sigma sub a. And sigma sub a is now the sum of our pole, real parts of our poles. We have 2 at the origin. Those don't introduce anything. We have 1 at minus 1. We have another one at plus 1. We have no finite zeros, and we divide by the pole 0 excess. Well, that pole 0 excess in this centroid calculation doesn't matter because we have 1 minus 1, or 0. So in this case, our centroid is at the origin. The centroid angles, which will be asked in this next question. Let me just go on here. So identify in this question the angles or identify those that are in the answer of our asymptotes. And here I'm giving you the answer here, but let's just figure out where those are. We now know that our asymptote angles are 2L plus 1, or an odd multiple of our fundamental angle, which is 180 degrees divided by the pole zero excess. This pole zero excess is now the number of poles minus the number of finite zeros, or it's actually then the zeros at infinity. This is now 4 minus nothing, or it's 4. Or our asymptotes are going to be 180 divided by 4, or 90 divided by 2, or 45 degrees, odd multiples of 45 degrees, where the odd multiples, L, goes from 0, 1, 2, up to the number of our pole zero excess, which is 4 minus 1, or 3. So we now need to iterate all of these through these different indexed values of L. At L equal to 0, we have 45 degrees for phi sub A. When L is equal to 1, we then are looking at 3 times 45, or 135 degrees. When L is equal to 2, we now have 4 plus 1, or 5 times 45. So that's now 5 times 40 is 200, and then another 5 times 5, or 25. So this is 225. And these all should be symmetric, and they are looking like they are giving us what we would expect. And then we have 7 times 45, that's 280 plus 35, or I think that should be 315. So our asymptotes are there with these angles. We have one angle here, that's the 45. We have another angle there, that's the 135. We have another angle there, which is the 225, and we have our last angle there, which is 315. We now need to check all of those that are in this answer. We have 135. There's nothing at 180. There's nothing at 0. And there's nothing at 90. So those are the only two options. Those are the correct asymptote angles that are provided as possible solutions for this particular problem. And notice that these asymptotes are centered, or they're centroid, since this is the same system as what this system is. They are centered at the origin, as we had calculated before. We didn't need to know that to answer this problem, and we didn't need to know what the angles were to answer this question, but putting those two together allows us to then figure out what our root locus diagram would be looking like, because our root locus branches, we have 4 going off to infinity, would approach these asymptotes that I've drawn as blue lines here. Hopefully that now gets you ready for the second attempt on quiz number 7. Good luck.